Alright, section 8.2 deals with torque and balancing torque. Now the definition of torque is it's how effective a force is at rotating an object. How effective a force is at rotating an object. And let me give you 3 examples, and I like to do it with wrenches. And I'm going to draw 3 wrenches here. So, and I'll call this case 1, case 2, and case 3. In case 1, I've got 3 forces, A, B, and C, all pushing on my wrench. In case 2, I also have 3 forces. I've got a force pushing straight down, a force pushing straight sideways, and a force pushing at an angle. And in case 3, I've got 3 forces, A, B, and force C. Now, which is most effective in case 1? Well, it turns out A is most effective because it's farther away. In case 2, B is most effective because A isn't going to turn it. C is only a small amount of its force is actually going into turning. If all 3 of these forces are the same amount, B, because it's a right angle, is going to be most effective at rotating this wrench. Now over here, this one depends. It depends how far away these things are. So like let's say C is equal to 40 newtons, B is equal to 20 newtons, and A is equal to 10 newtons. But then these distances, let's say it's 30 centimeters. Nah, let's go 3. Make the math easy. 3 centimeters. Let's say B is 5 centimeters. And let's say A is 9 centimeters. Which one of these 3 is the most effective at rotating this wrench? Well, this brings us to torque. To actually find torque, you take the force perpendicular times the distance away from the center of rotation. So in each of these 3 cases, case A, B, and C, force times distance. In A, you have 90 newton centimeters of torque. In B, you've got 20 times 5, which is 100 newton centimeters. And then in case C, you have 40 times 3, which is 120 newton centimeters. So the most effective turning one in this case is C, because it has the most torque. And we find torque by taking force perpendicular times the distance. Now, what if you're not pushing perpendicular? For instance, what if you have a bicycle pedal and you're pushing down on it with a force of, let's say, 100 newtons. And let's say this bicycle tire is inclined at an angle of 30 degrees. And then let's also say that this bicycle tire is 30 centimeters long. What's the torque created here? Well, what we need to do is find the force perpendicular. This is the one, the force parallel to the lever arm. This is the lever arm right here. So what I'm going to do is kind of borrow from our inclined plane chapter and know that this is 30 degrees. So this one is going to be half of that using my secret ninja method. So that's going to be 50. And then I'm just going to take 100 times the sine of 30, and that's going to be 86.6, I believe. Oh, I'm sorry, 100 times the cosine of 30, 86.6. because the cosine is the adjacent over the hypotenuse. So this is going to be 86.6. So my torque in this case, force perpendicular at 86.6 times my distance, 30. So if I take 86.6 times 30, I get 2598 or 2600 Newton centimeters. Now I could have definitely, instead of 30, I could have used 0.3 meters and I would have gotten 26 Newton meters. That's another way to do it. But as long as your units are congruent, all is good. Now let's talk a second about balancing torque. Balancing torque is, I guess maybe I'll just do this by an example. There's an example problem in your book. Now I'm going to do example problem number 2 on page 204. And it's got two young ladies sitting on a seesaw. And the one, I don't know, Carrie Ann is 56 kilograms and Aisha is 43. And it says, where are you going to place the pivot? And I know that I'm going to place it closer to Carrie Ann and Aisha over here. I'll just put a K and an A. And they do tell me in the problem that it's 1.75 meters long. So here's what I'm going to do. The steps to solving something like this. I'm going to label forces. So the first thing I'm going to do is figure out the forces. I know that each of these girls are exerting a force straight down, a force due to gravity. So if I take 43 times 9.8, I get 421 newtons. And if I take 56 times 9.8, I get 549. Those are not the only things. If those were the only things pulling down, these girls would be flying towards the center of the earth. Something is pushing up, and it's pushing up right there. And so you just add those two, 549 plus 421, and you get 970 newtons. So the question is, where? Where do we put this? And I'm just going to define that length as x. Step 2, equilibrium. When we've got equilibrium, these girls, assuming that they're balancing, they are in equilibrium. And equilibrium means a couple of things. The first thing it means is the net force is 0. Everything pulling down equals everything pushing up, which I've got over here. The other thing that equilibrium means is that the net torque is 0, that everything twisting it clockwise equals everything twisting it counterclockwise. Everything twisting this thing clockwise equals everything twisting counterclockwise. So sometimes I'll do this. This is just a little bit of Greek here. You add up all the torques that are clockwise, and they have to equal the added summation of all the torques that are counterclockwise. So that's what I'm going to do over here. I'm going to take this idea and apply it to my problem. Everything that twists this thing counterclockwise is going to equal everything that twists this thing clockwise. Now, when you look at your picture, first I have to define a pivot. Here's my next step. Define a pivot. I'm going to put my pivot right here. because that's what seesaws do. Believe it or not, you can actually put the pivot anywhere you like. I'm going to put it here because conceptually that's what seesaws do, is they pivot on that fulcrum. So if this is the pivot, then this girl, Carrie Ann, is cranking this whole seesaw this way, and Aisha is cranking the seesaw that way. This is a clockwise torque. This one is a counterclockwise torque. So what I do is I take the force times the distance. The force is 549 and the distance is x. Over here you take the force, 421, times this distance. The distance from here to the pivot. Now that's tricky. What it is 1.75 minus x. That's the distance right there. Because the whole thing is 1.75, and if I told you the distance from here to here is 1, that has to be 0.75. You just subtract it. And now this is just a creative bit of algebra that we're going to do. So 549x equals, I'm going to distribute 421 times 1.75. I get 737 minus 421x. So now I'm going to add the 421. So 549 plus 421. I get 970x equals 737. So x equals 737 divided by 970. And that's 0.76. And that makes sense because it should be closer. This should be less than half. Like half of this thing is 0.875. So you know it's got to be less than 0.875 because the heavier one's over here on the left. So that makes sense. So I'm going to say 0.76 meters from Carrie Ann. Now, to summarize this, to summarize everything, now, well, maybe not summarize just yet. You've got a couple of problems that they get kind of confusing when you look at them. So I'm looking on the practice problems. You've got a couple of hanging masses. This is a balancing of torques problem. This one on the right cranks it clockwise. This torque over here cranks it counterclockwise. And if they're balancing, those torques have to be equal. There's a problem with a bicycle pedal, and it looks really crazy because there's just so much going on. But really, what's going on is you're pushing on this pedal, and you're creating a clockwise moment around the center of rotation, and the chain is resisting you, which is creating a counterclockwise moment about the center of rotation. So you have to just balance those torques. So this torque is going to equal that torque, and that's basically what I did right here. Torque, torque, clockwise, counterclockwise, that's how they equal. Kind of just to wrap this all up, we talked today about torques and balancing torques. You can find the torque by taking the force perpendicular times the distance. The farther away you are, the more leverage you have, and if you're pushing at a right angle, you have more leverage also. Balancing torques, clockwise equal counterclockwise. Define a pivot if it makes sense. If it's a seesaw, just put your pivot wherever it pivots at. And then we utilized equilibrium. Clockwise equal counterclockwise, force up equal force down.